Hi, everybody. Welcome to this recording for Unit 34. Unit 34 deals with the structure of the solar system. It's an overview. So basically, what we will see the main locations and features of the solar system, and then the orbital rotation, and we see that there are some similarities between the motion of most of the planets. There are some exceptions that require some sort of explanations. So we could come up with a theory of how the solar system basically formed and how the solar system behaves according to the theory, and then try to explain basically any kind of odd thing. Also calculate the density of, or at least see how the density is calculated for some of this solar system components, namely the planets and even the sun. And based on the density, we will basically infer the structure of those planets, okay? Or those objects in general. So again, the solar system is mainly the sun, by far. And then, in addition to the sun, you have these 8 planets. You have terrestrial planets, there are 4 of them, and you have Jovian planets, similar to Jupiter, that's what the Jovian stands for, that they are mainly gas, and they are actually the outer planets. So there is a boundary between Mars and Jupiter, where it seems like the structure changes between big, giant, gas giants, and then terrestrial, smaller planets. There are 8 of them. In addition to that, we have dwarf planets. Dwarf planets, there are a lot, okay? You have mentioned in here Pluto, Ceres, Eris, Makemake, and so on and so forth. Haumea, and many, many other, about slightly more than a dozen dwarf planets. In addition to that, we have moons, and we have a lot of moons. Some of these moons are so big that they're even bigger than some of the planets, okay? And then in addition to that, we have asteroids that reside mainly in 2 regions. The asteroid belt between Jupiter and Mars, and another one which is outside of the reach of Neptune. It's called, it's where actually Pluto is called the Kuiper belt. So those are the 2 basically. The structure is slightly different because this one are closer to the sun, so they are mainly rocky. The others are mainly ice. But basically that they are all of this object that I just mentioned so far, they reside mainly on the same plane with the exception of dwarf planets. This is called the ecliptic plane. We need to explain that. We need to understand why is that so. And then, like I said, dwarf planets, in this case, some of them are actually odd things. They don't reside on that plane, so they orbit in a path that is a little bit at an angle with the ecliptic plane. And also, in addition to that, we have a structure that is far beyond Pluto and the Kuiper belt, and that is actually the Oort cloud. That is not on the same plane, definitely. That's actually more of a spherical structure. And that extends very, very far away from the sun. As a matter of fact, midway between it and the next star. Again, as I mentioned, the planets, they extend from the sun, basically starting from Mercury, Venus, Earth, Mars, and then there is the asteroid belt in here. In addition to the asteroid belt, which sits just between Jupiter and Mars, and it's a huge structure in terms of size, but in terms of mass, it's a very tiny one. As a matter of fact, Ceres, which is the biggest dwarf planet that sits in here, can amount to most of these objects added together. And that's a dwarf planet. In addition to that, as I mentioned, there is the Kuiper belt. The Kuiper belt exists well outside of, see here, the inner orbit is that of Jupiter, actually. So in other words, Earth, you can see it, it's well inside. And then you have Jupiter, Saturn, you have Uranus and Neptune. Anything outside of Neptune is called a trans-Neptunian object, or a TNO. And that's where the Kuiper belt is. And that's actually where most of the dwarf planets are, okay? Namely Pluto, Eris, I see here, what is it, Makemake and Haumea, and there are Sedna and other structures there, the other dwarf planets, they exist in here. Now, in addition to that, we see a comet that is originating from the Kuiper belt and goes all the way to the sun and comes back. And that is actually Halley's Comet that was discovered in the 1600s, okay? Or actually the 1700s, the 18th century, okay? So anyway, so the point being in here is that it takes about 76 years to come back around the sun. So again, these are some of the objects that reside nearby the sun. Some of these, as I said, all of them, or at least, exist on the same plane called the ecliptic plane. The odd thing in here is that the stuff that is on the Kuiper belt, they may not be on the same plane, make an angle. So dwarf planets doesn't mean that they are negligible. As a matter of fact, they are universes of their own. They have planets. Like, for example, Pluto has 5 moons. Haumea has at least 2 that we know of. Eris and Makemake each have 1. But the point being in here is that each of these planets actually has 1, so it's not like both of them have 1. As a matter of fact, they are separate dwarf planets. So the point being in here is that these are complete universes of their own. Haumea has a very, very interesting structure. Some of them, they even have rings, okay? So the fact that you are a dwarf planet doesn't mean that you're not a planet. You are still a planet. And so that's something that we're going to discuss exactly what happened in here. And that is when Pluto was discovered in the early 1900s. And it was discovered because Percival Lowell thought that there is actually another planet the same size of the Earth or bigger, and then he was hunting for it. So he spent all of his wealth on an observatory in northern Arizona, near Flagstaff, and that's where Pluto was discovered. Okay, I know Pluto has a name that's related to the Greek mythology, but the thing is, his name is actually hinted in the name of the planet too. Percival Lowell, so the first 2 letters. Anyway, but he didn't discover it. Actually, one of the people who were working in there, I forgot his name right now. I don't want to mess up his name. It starts with a Baugh. So, anyway, it's on the tongue of my mouth. I lost it. Anyway, the point being in here that Pluto was thought to be a planet, and then it was fine. We have 9 planets. There was no problem with it, albeit later on the size was determined to be a lot smaller than what we thought, because we discovered immediately a moon that orbits it, the moon Charon that orbits it. So we determined its mass. It's a very tiny object. Afterwards, more of these objects started to show up. Actually, Sirius was discovered around before that. Okay, and then we have another one, Eris, Makemake. More objects start to show up, and the list starts to grow very big. So astronomers thought, okay, maybe we should come up with a different classification just to simplify things. 8 planets is easy to remember. 27 planets is too much. So they came up with a definition of what the planet need to be, and the planet has to be, of course, big enough to be spherical in shape, and all of them are. With the exception of Haumea, as I said, it's like more of an oval shape because of the fact it spins super fast on its axis. And then it also must clear its own path. And that definition does not fit with Pluto. You're saying, okay, why can't we make an exception just below Pluto? Well, Eris is bigger. So if we're going to keep Pluto, then Eris must be also kept. And then the other thing also is, what if down the road we discover 27 of them, they're all of the same size or bigger than Pluto? So again, we made that decision, astronomers made that decision to make the cutoff there. And now Pluto is demoted because its path is in the Kuiper Belt, and the Kuiper Belt is full of all kinds of debris in there. Okay. So in 2006, basically, Pluto was demoted. But now, honestly, there is a talk to bring it back, not only it, but a lot of these dwarf planets, because there is, as I was saying earlier, these are interesting systems, universes of their own. They're actually far more probably interesting than some of the planets. Case in point, Mercury. Okay, as a matter of fact, Mercury, as I mentioned, is smaller than some of the moons. Okay, anyway, outside of that, around 50,000 astronomical units. That's very, very far. What you're looking in here is the blue line is Neptune, the furthest planet that we couldn't even discover, we cannot even see with the naked eye, okay, is well inside the structure. And then you have the Kuiper Belt, and after the Kuiper Belt comes a huge structure that was theorized and later on confirmed through observations of comets that come from that region. And so it's a huge structure. It must be spherical in shape because of the fact that the gravity of the gravity of the sun, that's the main dominant player in here. The gravity of the sun drops like 1 over distance squared. Gravity in general drops like 1 over distance squared. So at that distance, the gravity is super weak, that any interaction will throw the object in every which direction. So in this case, you have spherical structure. This one extends all the way to 100,000 astronomical units. That's a light year. That's midway between here and the next star, basically. Okay. So it's a super, super big structure, and it's mainly of smaller objects, icy objects, frozen objects, And some of the comets that come from that region, probably this is the first time. As a matter of fact, this year there will be a comet that's probably its first time that's going to arrive near the sun, because it takes a long time for them to come in here and then go back. Okay, so some of them probably were made one trip, or they're about to make their first trip. Okay, their existence in here for billions of years undisturbed, and then for the next tiny interaction, they get thrown out of their orbit, either out or into the sun. And once they start that journey, it takes a long time for them to go around the sun. Okay, so again, as I mentioned before, most of the planets, they exist on the same plane, called the ecliptic plane. And that's similar. So the theory here is that when you take a dough, for example, and you start to spin it fast enough to make pizza, for example, it flattens. That is due to the conservation of angular momentum. That's the magnitude of the angular, I'm sorry, the direction of the angular momentum. So when it's conserved, that means everything else is going to stay on the plane, because the angular momentum is actually a vector, and that vector is actually normal to the plane where it's measured. I'm sorry, the cat is in here, so that's why you're here. So anyway, the point being in here is that the conservation of angular momentum. So what happens to objects that really don't obey this, that their when they're slightly on and off? Well, in this case, probably immediately after the solar system formed, there were a lot of debris here and there, so there were interactions and collisions that caused these objects to go slightly on and off. But the smaller objects that are far away from the sun, any tiny perturbation in their path will cause them to move further. And that's why you see all of the dwarf planets that exist in the Kuiper belt, basically they are completely making a huge angle between them and so if this is the ecliptic, this is their path. Okay, so they are making a path that is kind of a big angle with respect to the ecliptic plane. So again, it has to do with angular momentum, and then to support that idea also is the direction of rotation. Almost all of them, they move in a counterclockwise direction, number one. Number two, they spin also in counterclockwise direction. That means the direction of the angular momentum also from that initial spin was conserved. Well, if you look at the path in here of all of them, they're almost making a 90-degree angle, basically perpendicular. They're making a 0-degree angle because the angular momentum is perpendicular to the plane. So they're actually making a 0-degree angle with the angular momentum. The sun makes 7 degrees. So that initial position was probably perturbed by the initial interactions. Mercury, 0 degrees, perfect. Okay. Skip Venus. Earth is slightly tilted, so something must have happened early on in the Earth to cause it to make 23 degrees. Same thing with Mars. Slightly off for Ceres, which is a dwarf planet between these two. And then Jupiter is 3.1 degrees, so slightly any kind of things, it was minor. Saturn, almost the same effect that happened to the Earth and Mars. Skip Uranus for a moment. And then Neptune, it's the same story for everybody else except Jupiter. And then you have Pluto. Pluto is dwarf planet, and all of the other planets we don't talk about because they're too tiny, and any kind of perturbation would cause them to go all over the place. Okay, so all of them, they're pointing mainly in this direction. So that can be explained perfectly with the angular momentum hypothesis and the fact that the solar system was formed. And when it formed from this big cloud that came together due to gravity, the angular momentum was conserved, hence on the same plane in terms of direction, and also in terms of magnitude because of the fact that all of them spinning in the same direction with the rotation and also revolution. Now, the point being in here is what in the world is going on with Uranus and especially Venus? Well, Venus, instead of spinning like this, spinning like that, it's almost 180 degrees. 177 degrees is almost 180 degrees. And then Uranus is on its side, actually, 90 degrees, slightly more than 90 degrees. So in this case, the collisions that this two objects probably in the early formation of the solar system was so big that it caused Venus to flip on its side and slow down. The day on Venus is super long because its rotation is extremely slow. That's one thing. Uranus split on its side. It's like you take a wheel, basically. So it's on its side. Remember, Uranus is huge compared to Venus. So probably the collision that both of them were subjugated to were big, but relatively speaking, you can't say that while Venus was subjugated to a more collision with a bigger object because it was smaller in size. So again, you can come up with a hypothesis and explain these things after the fact that the solar system formed, and then all of these things can be explained with the after effects interactions. Okay, I mentioned before that we're going to measure the density, and the density is critical in determining the mass of this. The composition of this object or structure of this object. Well, the first thing is the volume. If I know the distance, or I can estimate the distance to that object, okay, number one. Number two, if I can, basically the distance is just the period, how long it takes for a planet to go around the sun, okay? Go back to Kepler's law. Once you find the period, you have found the distance. Remember, a cubed is equal to p squared, where a in astronomical units and p in time. So all I have to do is just observe an object today. After 3 months, for example, see making this angle. Based on those measurements, I can infer how long will it take for it to go once around the sun. Once I find p, I found the distance. So I can find the distance to the object, this distance d. Then I take a coin and put it just enough to cover that object, okay? That gives me the angular size, the angle in here. Then use a simple of trig relationships and find the radius, the size of the object. So I have a size of the object, all of this planet. So I know what's its diameter, I know what's its radius. Then I use a formula for the volume, 4 pi over 3 r cubed, so I know the volume of that planet. Put that aside. Then I need to determine the mass. If I were successful in finding an object orbiting that planet, like for example the case of Jupiter, we have actually 4 moons that were discovered immediately. Io, Europa, Ganymede, and Callisto, they all orbit within days. Callisto orbits about 17 days. Io orbits within 2 days around it. So we have that in addition to if we can find the estimate to the distance between these moons and Jupiter. We use the same relationship I mentioned before to find the radius size, but this time around to find the mass of that object. But we use a modified version of Kepler's law to find the mass of that object. By the way, for those taking the lab, this is a lab. In the lab, we observe the 4 moons of Jupiter over an extended period of time and determine their distance in terms of the size of Jupiter, and then determine their period, how long it takes for them to go back and forth with respect to Jupiter. And then based on that, we plug in the value of P in here, we can plug in the value of D here, the distance of this moon. So Jupiter, 4 is number, pi is a number, when you square it, it's going to be a number. G is a constant, 6.67 times 10 to the negative 11. So you plug in all of these things, you'll find the mass of Jupiter. That's the lab. And that's what you do for all of the other planets. Now, imagine you have the mass of the planet through this method. You have the volume of the planet through that method. Now I can determine the density. Why is that important? Because the density tells me roughly what the planet is made up of. So running all of these numbers, basically, first of all, this is an explanation of what I was talking. This is just a little bit in detail than what I was explaining. So again, now we have an idea of what these planets are. All of the inner planets are rocky planets, including the moon, by the way. All of the outer structure is mainly gas because the density is super low. As a matter of fact, for Jupiter, it's 1.29. For the case of Saturn, it's actually less than 1. Okay, 1 kilogram per liter or 1 gram per cubic centimeter, it doesn't matter. The Earth is actually the densest object in the solar system, and we have a clear understanding of its structure with an inner core, solid inner core, liquid, not liquid, what you call it, melted outer core, and then you have the mantle and you have the crust. So we have that through seismology, through the earthquakes. We also landed a probe on Mars in 2017 that also detects earthquakes. So we have actually a little bit better understanding. We have more data on Mars. Same thing for the moon. These are based on models, okay? Understanding of how the structures are. So they are all rocky. The density of the Earth is the highest, 5.5. That of Mercury is 5.3. So give me an idea of that. Mercury, basically, it's mainly iron core and nickel in its structure. It's mainly a core. Venus is similar to the Earth. Okay, we have this model for it, and it works so far. Unless it breaks, then we have to revise this model. For the case of these planets, the outer planets, again, the cores must be, because that's the theory that I mentioned earlier for the formation of the solar system. That's all true also for the outer objects. So a rocky, iron, mainly nickel core that formed from the planetesimals that were existing there, that were through gravity, started to coalesce because of their high density. Then they started to grab materials more and more. Because this object happened to be beyond the frost line, so they gathered more water. They gathered in the form of ice, of course. They gathered more gases, methane, and also oxygen and hydrogen, and that explains their density being so low. So that's basically what the value of this thing. Again, all of these are models. Nobody really have a supported data, at least hardcore data to support the structures, but there is evidence for this models. It's not just a kind of a, as a matter of fact, again, Mercury is mainly core of iron and nickel. Venus, because of its similarity with the Earth, and we know exactly how Earth is structured, okay? They have a Mars-sized iron nickel core. And then the moon is also because we have more data on it. And Mars, again, we're just getting more and more data actually to support what we know about it. Okay, roughly half radius. And then it's a moon-sized basically core. And then they have a mantle and so on and so forth. Okay, and also it can explain the magnetic field properties of these ones in here. Okay, because of the slow motion of Venus, although it has a high big core in there, it does not have a strong magnetic field. So because the magnetic field will depend on the current in this case, not just an iron core, but also the rotation, the speed with which it moves. For the case of Mars, it moves fast, but because it has a day which is 24 hours, roughly slightly more than the Earth's day, but slightly slower, I should say. The day is slightly longer. But it doesn't mean, it does not have a magnetic field, so the core must be basically a lot smaller. Okay. For Jupiter and Saturn, they have a big iron core, and that does not explain their magnetic field. So they must have something else, and hence the liquid metallic hydrogen that explains their strong magnetic field. Okay, hydrogen can behave like a metal in this form, and metals can, when they're in motion, they generate magnetic fields, just like currents. So in this case, this is basically how the structure can be explained. And Uranus and Neptune, again, these are the models that we have for them in terms of their structure. Okay, we're going to go a little bit more details down the road in some of these units. Thank you.